everything, but unfortunately I got stuck in the that big storm coming back in the desert. So was a little bit dicey coming back, but I made it back okay. And so I thought just in case, I didn't want to take any chances. I better stay remote. So excuse me if I make a little bit of extra noise during the talk at the same time, but I'll do my best to get through it. So as Gary has said, and I believe Ron also, that yeah, this is a talk on electromagnetic pulses, otherwise known as EMPs, cloaking and seismic activity. Can everyone see my screen okay?
Yes.
Great, awesome. Okay, so let's go and get started. So going back a couple weeks, we had a very large EMP hit from a sunspot in the southern hemisphere, and you can kind of see where it's highlighted over here. That's Australia and Indonesia. That was the main area of where this solar flare slash EMP slash plasma ball, there are many different names for the same thing, where it actually hit, and you can kind of see the outline of it. And it did have quite a bit of disruptive activity in that area when it came to satellite transmissions and cell phones and whatnot. And you can kind of see, looking over at just these graphs that I have over here, you can see where there's the solar X-ray activity is greatly increased, and that it's actually produced this whole line of geomagnetic activity. It's affecting, again, the magnetic field of the Earth at that particular point, and going out from the like in concentric circles from where Australia and Indonesia is, it gets slightly less strong, but you can still see where it's still affecting around the belt in the ocean over there and in that particular area. So yeah, definitely. And then right below it, I have just a shot of this solar flare showing it in scale with the Earth. If you guys, everyone can kind of see the Earth right next to it right there.
Yeah.
That's an example of how large one of these solar flares can be in reference to us. So we're wondering, well, why is this affecting us from the sun? Well, you just look at the scale of this. This could completely, we get one large enough and in the correct direction, this could completely envelope the Earth with an electromagnetic pulse. So, and then not only do we have a very large solar flare, but we also have been having increased seismic activity. If we notice, there was an earthquake around the same time. Actually, it was a few days afterwards in Malibu. And then in addition to that, we had another one recently over in the Ontario area, I think near the airport. And one of the things I'm going to discuss tonight is there a relationship between these two things, between EMPs and solar flares and increased seismic activity? And that's something that I'm going to be part of this discussion. So we'll explore that a little bit as we get into it, and what the reasons are behind that. Like this is a hypothesis that I'm putting forward, but it's also one that's been explored by other researchers as well. Okay, so what is an electromagnetic pulse? Well, thank you, Wikipedia. An electromagnetic pulse, EMP, is also referred to as transient electromagnetic disturbance. It's a brief burst of electromagnetic energy could be from the sun, but it could be artificial. And we'll see that here in a minute, where it's being created by other things besides the sun, and can be electromagnetic or just electric and magnetic and conductive at the same time. It can disrupt communications and damage electronic equipment. And certainly, you know about lightning strikes that can physically damage buildings and things like that. Well, working for Edison, we're very familiar with some of the damage that lightning can do to our structures, our transformers, and other assets that we have out there. So we have a lot of mitigations that we have already put into place for that. But we'll look at some of these other ones in continuous. And that it deals with what they call EMC engineering, electromagnetic compatibility engineering. And the first major event that was recorded was the Carrington event, which was in August of 1859. and that had at the time mainly any sort of electromagnetic devices that were being used were telegraph machines, and it did disrupt quite a few of those. So just kind of a brief overview. And I'm going to be pulling some information from this report that was done by a person named George Lane, who is Director of Chemical Security and Emergency Response. And he's did this for the Homeland Defense and Security Summit. So this is where he's discussing the effects and responses of EMPs. And again, he's talking about EMPs being an intense burst of electromagnetic energy caused by this rapid acceleration of charged particles that can destroy or damage electronic systems, primarily by overloading circuits, but there's other ways that this can happen, and we'll look at that here in a minute. And EMPs are caused by these whether it's geomagnetic coming from the sun, like in a coronal mass ejection, a CME, or also by the atmospheric detonation of nuclear weapons. Those are the two primary ways that they see this happening. These EMPs are being created. And direct exposure to EMPs is pretty much harmless to people, but however, it can affect much of this critical infrastructure in things like the power grid, communications, transportation, and many, many other things. And again, this is all based on this report that he did for the Homeland Security Defense and Education Institute. And it has to do with nuclear EMPs are characterized by a range of spectrum of frequencies. The waveform shape itself that's produced, and the duration and amplitude of that particular waveform when an EMP is created by a nuclear weapon. And we'll break that down a little bit here in a couple more slides. There's different types of the waves and how they're affected in the length of the wavelength, and if they're short waves or long waves, and short term or longer term, and what the different effects of those are. But a nuclear weapon detonated between 40 and 400 kilometers above the ground can generate an EMP that could hypothetically, again, knock out about 70% of the US electric power grid. And that depends on the intensity of the detonation, but it is a possibility. It's definitely within the realm of possibility. And the sun generates EMPs and solar flares that can cause these geomagnetic disturbances. Solar coronal holes and coronal mass ejections produce these magnetic disturbances coming from the sun. And normally these are low frequency that take a few days to reach the Earth if they're lower frequency and they're not necessarily traveling at the speed of light. And what they can do, which is interesting, is they energize long power lines. And what they do is they actually make that power line become a conductor for the charged particles that reach the Earth. So, okay, I think we already saw that one. Sorry. So here's just a little diagram of what it looks like when we're getting a coronal mass ejection from a solar flare that turns into an EMP when it hits the Earth's magnetic field. And you have the sun on the left, and here's a solar flare. They're generating these charged particles, gamma and X-rays and other things depending on the spectrum frequency. And it's hitting the Earth's, first it hits the outer heliosphere, and then depending on the strength and the intensity, it reaches the magnetosphere, and then finally the ionosphere. And that's where we're getting a lot of the, what we would call aurora borealis. Normally it happens in the polarities, like the North and the South Pole of the Earth, because that's where the magnetic field is the strongest and the most intense. And we normally see those in the North and the South Pole when there is higher solar activity as far as coronal mass ejections. They may not necessarily be an EMP per se, because they're not affecting anything. They're just producing the auroras and things like that by these charged particles hitting the magnetosphere of the Earth, kind of like the charged particles hitting inside a TV screen and causing the screen to glow. It's kind of the same principle. And we'll see as we get larger and larger CMEs coming from the sun, we'll begin to see um, more and more aurora borealis, not only at the poles, but at lower latitudes, even near the equator. That happens if the energy of the particles is strong enough. And here is just a brief history, again, talking about the Carrington event in 1859, when Richard Carrington, who was an astronomer, was capturing these images of sunspots. He noticed that there's two brilliant white lights suddenly appeared over the sunspots and intensified. And he didn't realize it at the time, but those were the CMEs, the coronal mass ejections, that would hit the Earth as an EMP. And part of the effects of that were not only, affecting the telegraph and some of the other simple communications they had at the time, but in addition to that, they noticed skies all over the Earth erupted in red, green, and purple auroras. So brilliant that people could read newspapers at night in Cuba, the Bahamas, Jamaica, El Salvador, and Hawaii. Well, those are all near or at the equator. So if you're having that strong of an effect on the magnetic field at the equator, it's going to be much stronger at the poles of the Earth. So you could only imagine what was happening there. And they said even when the telegraphers disconnected batteries, that the aurora-induced electric currents still transmitted the messages. So I just thought that was really fascinating, that even when they weren't powering the telegraph machines themselves, there was enough electricity within the atmosphere around them, around the air around them, that they could actually still send messages through the telegraph machine without it being connected to its batteries. I just thought that was it was really fascinating. And here's an example of one that we had in 1989, where you can kind of see the overlap of the geomagnetic storm, again, the CME, and it turned into an EMP. And if you can look towards the bottom of the intensity, you can kind of see it's reaching almost into possibly Northern California, and then going down even to some of the eastern states and whatnot. Reasonably strong one, but wasn't quite as strong as a Carrington event. This was on March 13th, 1989, that this one actually happened. So you kind of see the overlap of where the strength of that geomagnetic storm hit the Earth and caused the EMP. Okay, so let's talk a little bit about the nuclear side of this. And during the first nuclear test on July 16, 1945, that was Trinity, again, out in Los Alamos in the desert in New Mexico. They shielded electronics because there was Dr. Enrico Fermi, who was one of the physicists that worked on the Manhattan Project there. And he also was a Nobel Prize recipient for coming up with induced radioactivity, said that he actually predicted that they would have an electromagnetic pulse happening when they detonated the first nuclear bomb there. And so he said that even though they did do some shielding and whatnot, that some of the electronics were still damaged. And then there was an effect that came up that wasn't predicted by anybody, including Fermi, where an artificial radiation belt was created just by the EMP itself. Now, what this is, an artificial radiation belt, is a torus. Now, what a torus is, if you're not familiar with it, it's a shape, it looks like a donut in certain dimensional shapes, but when it's in 3 dimensions, it's shaped like a donut, so it has a hole in the center of it. You go down in dimensionality, it actually becomes a circle, but it's one of the more common shapes in nature, and we see it a lot in physics and mathematics, and I use it a lot in my work and whatnot. But it's a surface that's formed when you rotate a circle, basically around a circular path, you form a donut. And this is what forms in a lot of different situations when you're dealing with things like fusion, electromagnetic energy. The field itself will form a torus. So this is what happened, is this EMP actually formed its own artificial torus, and it can actually cause a miniature EMP. It's not as large or as strong as one that would be coming from the sun or whatnot, but it can actually form a torus that, if like a satellite passes through part of that donut, it can damage the satellite's electronics. And so they realized this, and then they started doing some tests on this just to see what type of EMPs we would have with different nuclear devices. And there's one they did a test in this experiment called Operation Hardtack, where they actually collected data, and they found out that a higher altitude EMP could be more intense and do more damage than one that's low, because of the fact that that EMP, the pulse, is going to be spread out over a much larger area, because again, it's being spread out from a higher elevation, and that the ground is actually acting as a radiation absorber and conductor at the surface of the Earth. And we'll see why that can be problematic as well for a lot of electronic devices. But they also figured out that this was only a small one that they used. It was only 1.7 kilotons and launched by a balloon, but it still had that same effect. Now, Trinity, which was again the one from the Manhattan Project, had about 15 kilotons. So it was orders of magnitude greater, and they can imagine that that was a high altitude EMP just with that Trinity. And again, the nuclear devices we have now are many orders of magnitude stronger than 15 kilotons, in the thousands, some of them. And just even a smaller one that would be only 1.7 could still do quite a bit of damage. So here's an example of what the artificial toroid torus radiation belt would look like, produced by the EMP. And you can kind of see how it goes around, forming its own magnetic field line, kind of going around the Earth here. And then if there is, a satellite's unfortunate enough to pass through that, it can affect its communication and things like that at one point. And again, this is kind of a short-term effect, but it's still enough to be able to knock out a lot of communications and things like that. Okay, so let's look at kind of categorizing some of these. And types of hemp, it's not a plant, that's actually high altitude EMP. That's what that stands for. But if you start over at the left, we have what's called the E1, that's the early time, and you're kind of in, less than a second, like 10 to the negative 10 seconds up until 10 to the negative 6 seconds. That's where you're getting a lot of gamma signals, gamma rays coming through. They're very fast and moving, at tens of thousands of volts per meter. And then you get to the E2, which is the intermediate time, where it's getting more scattered and you're getting more kind of neutron signals, a little bit slower, going from about 10 to the minus 6 till about 10 seconds or so. And then finally you get what are called the late time, the E3s, and we'll see what the effects are. Those are the slower waveforms. They're more than gamma and neutron waves signals. They're more like magnetohydrodynamic signals. So they're kind of right within the electromagnetic spectrum, and they're usually from 10 seconds on, sometimes into the days or weeks, depending on the strength of the signal. And we'll see kind of how each of these are going to affect what we have out there as far as like electronic devices and other things. But those are kind of the three basic categories. You got the early time, again, with about 10 to the negative 10 to about 10 to the negative 6 seconds. The E2 intermediate times, which are a mix of gamma and neutron waves from 10 to the negative 6 to about 10 seconds. And then the E3 late times from about 10 to sometimes days, as far as their signal time and whatnot, how they affect. So you can talk about EMPs having a field strength up to about 50,000 volts per meter in 5 nanoseconds, and over a period of 100 nanoseconds, it tapers off to a background noise. And the E1 pulse, again, that's that first one, that really fast one, that's about within the 5 nanoseconds. It's brief, but it's very intense. It has a lot of gamma rays in it because it's moving very fast, and can induce very high voltages in conductors and transformers, as long as they're within the line of sight. It's kind of, I think, part of what was happening in Australia, down there in Indonesia, with the issues that they were having with that latest EMP. And lightning surge doesn't work on it, like surge protection and things like that, because it's moving too fast, and it's mainly gamma radiation. It's not standard electromagnetic radiation. So it's moving too fast for any sort of lightning surge protection. So it's the disturbance, what they call a starfish prime, was due to the Compton effect. That was basically another EMP, and it caused auroras in Hawaii at the time. And then there's a physicist, Dr. Arthur Compton, that said that he thought it is because there was electrons, that the photons were removing electrons from atoms in low atomic numbers. So in other words, if you have like a low atomic number, that the gamma radiation would produced in a nuclear explosion would knock the electrons from like oxygen and nitrogen atoms, because those are lower atomic number atoms in the atmosphere. So Compton was the one that said that that's why this was happening, that these pulses would be able to remove electrons from these atoms with lower numbers. Excuse me. So that's part of the E1, again, the real fast and intense part. The E2 component is generated by scattered gamma rays, and the inelastic gamma is produced by, again, the neutrons, because it's slowing down a little bit. And they go from about 1 microsecond to about 1 second, or about 10 seconds. And then these are okay. They fit within the spectrum of lightning pulses. So you're able to use lightning surge protection for those. Is you couldn't do it with the E1, it was just too fast, but it'll work for the E2. And then we get to the E3, and that's the pulse which generated by either the fireball expanding and collapsing if it's a nuclear explosion, or also the actual plasma ball coming from the EMP, from the coronal mass ejection of the sun. And this is what's causing the Earth's magnetic field to actually oscillate and move back and forth. It's not as much of a freely propagating wave like an E1 or an E2, but it's more like something that can last minutes. So it's more like a magnetic disturbance in the field that can last for quite a few minutes or even longer. And it's a low frequency pulse. So what does that mean? Well, when you have a lower frequency pulse, it's able to penetrate things like the ground. So an E1 or an E2 couldn't do that. It's the frequency is too high. And you'll notice this, you think of when you hear music from someplace like in the other room, you'll notice you can hear a bass sound, but you can't necessarily hear the higher frequencies in the music, like maybe somebody singing, because those higher frequencies don't penetrate through solid objects, but a lower frequency will. I've got some colleagues, some friends of mine that are actually work in acoustics, one of the top acoustical sciences. And I talked to him about this, and he says, yeah, that he was basically, they use a lot of low frequency things that they're looking to penetrate through solid objects. It's actually something they do in the military as well. So it was just interesting to know. And so the E3 can actually penetrate through the ground, but when it does that, it's going to induce currents in buried cables. So underground cables are not necessarily safe from an E3 pulse. You think it would be. The E1 and E2, it doesn't do that. Again, frequency is too high. It'll just bounce off the ground. But an E3 will actually penetrate into the ground and can induce currents in cables that don't have any current running through them, which can affect a lot of different devices. And when this happens on power lines that are buried for miles long, it's enough, it can build up enough energy, enough voltage to actually burn up and melt transformers. So if you think of it that way, that's one of the damaging things that this low frequency pulse can do. If it's hitting in an area where it's actually able to activate or energize miles of underground cable, it can end up melting transformers. There's enough induced current in there and voltage to melt the transformer. So it says, again, an E1 alone cannot cripple a transformer, but with an E2 following the E1, that's enough collective energy to be able to do that. And an E3, again, the low frequency, longer duration pulse, can disrupt a lot of different things, especially in underground electric transmission lines. And again, they use this Operation Hardtack, where they used a very small nuclear device, only 1.7 kilotons. It doesn't take much to do this, especially if you're in an urban area that has a high concentration and a high intensity of different electronic devices, electrical devices, and it could knock a whole grid out, all the infrastructure and everything that's part of the grid, whether it's the cables themselves, overhead or underground, whether it's the transformers, the substations, and all the different devices. Okay, so talking a little bit about solar panels, there's ideas where they create what's called a Faraday cage around the solar panel. They basically, if you look at the diagram, what they're doing is they're putting kind of a shield around these solar panels, and that's what's they're still able to collect the solar energy, but they're shielded at the same time. So what's happening is that the fields inside the wall of that shield are actually canceling each other out, and that's neutralizing it. So it's not going to affect the solar panels in any way. It's, in other words, it's not going to induce a current in the solar panel. But this only works when they're protected while they're inside the cage. If they're not inside the cage, um, they're not protected. So this is one possibility they were looking at least for solar panels, to be able to shield them. And I thought this was kind of interesting. It was kind of amusing that they're showing that microwave ovens are shielded because of the radiation involved with using microwaves for cooking. That if you, they act as kind of their own Faraday cage, and if you wanted to, and you wanted to keep your devices safe like a cell phone, you could put them in the microwave ovens during an EMP. And I thought, just with the caveat that don't turn the oven on while they're in there, because then you might have another issue. So make sure not to, cook your bacon while you have your phone in your microwave, because that would cause, obviously, have the opposite effect. But it just kind of shows that they had different ideas, like how do we protect our devices from EMPs, and that was one possibility there, using the microwave. So on May 15, 2013, Federal Energy Regulatory Commission directed the North American Reliability Corporation, which is NERC. I deal with quite a bit of NERC documentation and a lot of their regulations and standards at Edison. So they were to come up with a set of reliability standards to address the impact of EMPs on the operation of the bulk power systems. They're just calling it a geomagnetic device. That's what it stands for. Or disturbances, actually. I'm sorry. Geomagnetic disturbance, but it's basically the same thing as an EMP. And NERC approved a standard to mitigate the effects of these by implementing plans, processes, and procedures. And it just talks about these primarily for E1 and E2 events on power transmission systems. But they really look at E3 because they can look at the long-term effects it would have, especially on underground cables. So I'm going to show some data that I was working on, but in addition to that, this is something I partnered with MISA, which is the Cal Poly Management Information Systems Student Association. Do we have anybody from MISA on the call on the presentation right now? Any MISA people? Okay. Well, MISA, I've last 3 or 4 years, I've mentored and advised them on their student analytics project. This is a student organization through Cal Poly. I've kind of been helped them out with coming up with their analytics projects, and served as kind of a mentor and advisor, being that I have a foot in both camps as far as Edison and Cal Poly goes, and coming up with some analytics projects that were related to energy and Edison and renewables and other things and whatnot. So what I'd like to do now is I'm going to share this data that I put together. Can everyone see that? See this Excel sheet? Okay, I'm hoping you can see this. So what this is,
Not seeing it.
okay, great, thank you, just awesome.
Yeah.
Awesome. So what this is I've done some research, and again, passing this off to the MISA team, they're helping me with this as well. There is a relationship between sunspot activity, which again can be EMPs, coronal mass ejections, and seismic activity. So I collected data from 1992 to 2014 to kind of match the data sets, monthly sunspot activity, whether it's from the northern or southern hemisphere of the sun, and the amount of monthly magnitude 6 or greater earthquakes throughout the Earth. So what this means is there's monthly data on the sunspot, how many sunspots we had coming from either the northern or the southern hemisphere of the sun, and the number of magnitude 6 or greater earthquakes. Now, it doesn't, the geography, we're kind of working on that. I've actually got a bunch of lat and longs that we're going to bring into the data set. But right now, we're just looking at seismic activity over the entire Earth. And what we found was ran a regression model and using the sunspot as the independent variable, the total daily sunspot numbers, but I converted those into months and used that compared to the dependent variable, which was the magnitude 6 or greater earthquakes. And there is a significant relationship between them. That means as sunspot activity increases, the seismic activity increases as well. And there's about a few days lag, and I'll show in a second another research paper on this that shows some of the correlations that they've done with their research, but they say it's approximately 14 days from when we get a sunspot, because sometimes it takes a little while to travel and hit the Earth, and then what we notice as increased seismic activity. And we notice it's nonlinear because there's a couple of outliers in the data here that kind of pull the data away from being linear. But I went ahead and looked at the average of the predicted, and then based off of that, I ran a predictive model, and the average of that is about 23 magnitude 6 or greater earthquakes per month. That's over the globe.
Hey, Scott?
Yes.
It looks like we're not seeing the slides.
Yeah, I think
You're not seeing that?
Can you share screen?
Stop for a while until we can get, yeah, they're talking to it.
Okay, sorry about that. Let me see why. Let me see if I can just share the file itself. I apologize. How about that? Can you see it now?
Yes.
Yeah, that's good.
There we go, you got it.
Great, awesome. Thank you. Thanks for letting me. Yeah, because sometimes I do it, and it sometimes it works when I just share my screen, and sometimes I have to share the actual document itself. But here's the regression model, and then I just call it rejecting the null hypothesis. That means there's a significant nonlinear relationship between the sunspot activity, and it says total daily sunspot, but I actually did it per month. I had to sum it up per month because we have to realize, again, there's a few day lag, at least according to other researcher hypothesis, that there's a few day lag between sunspot increase in sunspot activity and increase in seismic activity, but it does show a relationship there. And then this is just the plot. And if we look over here on the right, again, I've got the predicted based off of those values. It looks like predicted of greater magnitude 6 per month. It's about 23 is the average. And then we had a couple outliers of, that's what pulled it off of being, made it more nonlinear, is we ended up with a couple of really big outliers that were over like 100. And but if we look at the plot here right next to it, this orange line, that's if it was perfectly linear and it was a one-to-one relationship, that as one increased, the other one increased. That's what it would look like. But we do know that it is a significant relationship because of these two values over here, the t value, stat value, and the p value. The t stat value is really high and the p value is really low. And so because of that, we know it's really significant. It's just not quite linear in that sense. So this is kind of just an example of just pulling, and I got this data from the NOAA and NASA and also the USGS sites, just pulling this different data. Like here's some of the sunspot data. Here's my earthquake data that I created a pivot table with, and just had to kind of match them, and had to do a little bit of data transferring to get everything to match, to get it to monthlies, going from years to month. And then we're able to actually pull in some of this where we have, let me see, I'm sorry. Yeah, right here we have lat and long. So that's going to kind of be the next step we're going to work with on with the MISA team is we're going to start looking at actual locations of these events to see if there's a correlation in certain areas. And hopefully that can help us to get to the point where if we know there's increased sunspot activity, is there certain geographic areas that seem to have an increase in seismic activity. So any questions on that?
No.
Yeah.
Oh, yeah, one question.
Sure.
I was wondering, is there any hypothesis as to the mechanism for that?
Well, and I'll show the paper here in a second. The way that certain researchers think what's happening is when the charged particles are hitting the Earth, what they're doing is they're disturbing the magma in the around the Earth's core, and the magma is in a plasma state, and we'll see how that kind of fits into all this. The EMP itself is plasma, but it's disturbing the magma within the Earth. It's causing fluctuations and waves in the actual magma, and by doing so, when the magma starts to move more, well, it starts to move the Earth's crust, and then the tectonic plates start to shift.
Wow.
And there's a few day lag between that actually happening, but they're hypothesizing that what's happening is when an EMP hits a certain part of the Earth, that it's disturbing that magma, kind of just roughing it up a little bit, causing turbulence in it. And by doing so, once that turbulence goes, it kind of floats up into the tectonic plates and starts to shift those plates, and causing different fault lines to become more active.
That's incredible. Thank you.
Sure, no problem. So let me see if I can go back to this. Okay, can everyone see that okay, my slideshow again?
Yes.
Yes.
Okay, so this is one of those papers. This is the correlation between sunspot activity and large earthquakes worldwide. And again, all these I have links on. If anyone's interested, I could send you the presentation here, and all these are live links. You can get more information. I just kind of did a brief summary on these, and they're talking about large earthquakes occurring worldwide have been recognized to be non-Poisson distributed. Well, that just means they're not evenly distributed over time. There's obviously clusters of different areas that have larger numbers of seismic activity. And until now, they said that no statistically significant correlation could be found. In other words, they couldn't find out what's causing this. So what they did is analyze 20 years of proton density and velocity data as recorded by this satellite. And they found a clear correlation between the proton density, which is coming from the EMPs, and the occurrence of large earthquakes and they use greater than magnitude 5.6 with the time shift of 1 day. So they're saying between when the proton density is increasing on the Earth, a day later, there'll be an increase in earthquakes of 5.6 or greater. So this is the research that they actually published this in Nature. So it sounds pretty legitimate, what they were actually coming up with. So that was one paper. And then there's this other one, pre-earthquake unipolar electromagnetic pulses, where they're actually measuring these low frequency EMP that is occurring before earthquakes. And there was the Lumrock earthquake of 2007 that they actually used a magnetometer about 2 kilometers from the epicenter, recorded these pulses right before that earthquake happened. So not only are EMPs causing earthquakes, but earthquakes are causing EMPs. So they're affecting the geomagnetic field of the Earth as well. So again, another paper, got a link to the whole thing right here if anyone's interested. So that's kind of that. So what are we doing about all this stuff, or what are we trying to do? Well, microgrids is one way. If you're familiar with a microgrid, that's where we're doing like little grids within like a certain neighborhood where people are producing their own energy by solar panels or whatever else they're using. So that's one way, because if you get a microgrid and one shuts down, well, there's still a bunch of microgrids to kind of make up the difference in the area. And you can kind of use that as a way to, it's kind of localizing the effects much more than it would be. Another way is some of the things that I've been kind of doing on my own, somewhat with Edison and kind of independently as well, is to cloak in the shield transformers and other grid components. And I just call this my DIY plasma stuff, but I'll show what this is here in a second. And this is just kind of a simple diagram that I did. And what it's based on, if you start at the top, we're going to look at some things where I'm simulating. I want to say simulating because I don't have any radioactive material, but I'm kind of bringing together the scaled down versions of fusion reaction by using plasma electromagnetic pulses and shielding them with magnetic fields. And I'll show you how that actually is going to work. But that we're using the same devices, the same things for that, and creating this plasma propulsion thruster, which is creating a small scaled down EMP, and that we're actually shooting these EMPs at a shielding or cloaking device that's cloaking an electronic device. And in this particular case, what those are made out of are what are called metamaterials. And metamaterials, if you've ever heard the term before, are these devices that are made out of repeating patterns of certain conductive materials. And they're used for invisibility cloaking because they're actually used to cloak things around. What they'll do is if you wrap a metamaterial around something, it actually cloaks it either electromagnetic or acoustically so that you can't see or hear that. You can't detect that device. So what it's doing is it's kind of bending the light waves or the acoustical waves around something. And, this part of what I'm doing here is I'm using metamaterials to see if they'll not only shield and cloak devices, but they also collect the energy from the EMP and function is like solar cells collecting the energy. So it's kind of a twofold thing where they're collecting the energy and they're shielding and protecting it at the same time. And it's just I'm doing this as kind of a scaled down DIY tabletop version. And again, we'll see how the fusion reactor fits into this without the radioactive part of it, but just the electromagnetic part of creating the plasma and controlling it with with a magnetic field and how that plays into the propulsion thruster with the EMPs and whatnot. So this is kind of what I set up. Again, you think just kind of backyard or garage tinkering kind of stuff. But if you start on the left, I have these small Tesla coils that are creating the plasma. Again, that's lightning, the ionized air, creating the lightning out of the Tesla coil by using a large step-up transformer. And that we're using that plasma as a simulation of an actual fusion reactor shaped like a torus, again, the donut shape of the torus, by containing it within a magnetic field. But that same Tesla coil is also a propulsion device that's shooting the plasma lightning at this EMP cloaking test that we're doing. And right below it, I just got some of these devices. You can see there's a dome, this little magnetic torus-shaped device, which is actually a mini cyclotron that I have that has these magnetic fields that it can move this ball bearing around at very high speeds, kind of simulating a cyclotron, a particle accelerator, of course, just a much scaled down version of that uses super strong superconducting magnets to move particles around it and then smash it into other particles. Same principle, just much smaller energies and things. And then a Tesla coil below that. I've got a laser over here on the right, which I'm going to use to guide one of these Tesla coils into the cloaking device to see if it's actually working. And here is kind of my just very quick DIY tabletop bill of materials. Up here on the upper left, I've got 2 Tesla coils, one in a globe and one kind of from a lightning rod. Then the dome over here that's protecting that's going to fit over this magnetic coil. That's the torus right below it. That's going to produce the magnetic field that the Tesla coil will sit inside, and then I'll put the dome over it, and that's going to be the what they call the tokamak reactor, where the plasma from the being used to heat the radioactive material will be contained within the magnetic field. That's what they actually do in fusion reactors. And then over here on the upper right, that's my metamaterial cloaking device, which is called a split ring resonator. And you can see that it's got these repeating patterns on it. And you'll see how I'm going to do is I'm going to actually take this plasma lightning rod and shoot it at the cloaking device. and we'll see how that works. And then I'm going to have this laser towards the bottom. I've got another laser that's more powerful. This is kind of a less powerful one I'm going to use. And I'm going to shoot the laser at the plasma to guide it into the cloaking device, because the light beam will actually guide the plasma lightning coming from the Tesla coil. And then over finally, there's a smaller Tesla coil that I just built as a kit just to get familiar with it. I just wanted to practice my soldering skills, and then a couple of power supplies for all this stuff. So you can see it's, just really small scale down kind of tabletop stuff to play around with, to try out some of these principles. And then this is just another paper where they're showing how people are using metamaterials to create plasma, and that the plasma is being used to actually power small satellites and things like that, like the satellite propulsion and that sort of thing. And they're also using the metamaterials to create plasma, but they're also using plasma to create metamaterials. And I think I'm supposed to show a video here. Yeah, I'm going to try this out. I'm hoping this will work. I've got a video to show you, and I actually got two, and hopefully you can hear and see this. So I'm going to give this a try. And this is of me doing that first, that's going to be the plasma within the magnetic field, and you can see how that's going to work. And the second one is where I'm actually using the Tesla coil to shoot the plasma against the cloaking device. So let's give this a try. Notice something interesting. Let me see if I can turn up the volume here. Can everybody see that? See the video?
Yes.
Okay, great. And hopefully you'll be able to hear it as well. Let's try. And as I try and put the globe on, that we get kind of a reaction out of it. It was shutting down first. I'm just kind of watching it carefully, and it shuts off. It runs out of oxygen. But that we also notice that we're getting that. I don't know if the magnetic field's having any effect on it yet, but that's kind of a low frequency. You can smell the plasma, the ionized air as it's going. I don't want to leave it on too long in case it has a detrimental effect on the globe itself, on the dome, I should say. But here I just wanted to demonstrate kind of how it's the plasma field, EMP lightning being contained by the magnetic field, kind of a simulation of the of what it would be if this was an actual tokamak. You'll notice something interesting. Okay, any questions on that?
Yes. Hey.
So that needle that is vertical is moving, looks like slightly when the pulses are right.
I can't hear you. Yeah, I can't hear you, so I'm sure he can.
Oh, okay.
You can go up there.
I have to go up there.
No.
I'll just try to talk louder. It looks like the needle is as if the electromagnetic pulse is moving that needle along. When you see the electric lines like lightning, it seems to also be moving the needle. And why is that?
Well, that's actually where the plasma is coming from. If you think of it like a lightning rod, the plasma is actually kind of escaping from the end of the needle itself. So what happens is you're taking an electrical signal and you're stepping it up. It has what's called a step-up transformer in it, and you're increasing the voltage, and you're releasing it at very strong pulses. So when the pulse hits the air, it's all that electrical energy is kind of exploding. And that's what's causing the plasma. It's ionizing the air around it. It's actually electrically charging the air. And if you were to actually have that in front of you, you could smell it. It has this very distinct smell to it, almost like burning. If you ever burned a circuit board in a computer, it kind of has the same smell to it. And so what that's doing is it's ionizing the air around it, and the air is actually becoming electrically charged with the plasma, just like when a lightning bolt hits. It's kind of the same thing, if you want to think of it like that. This is like a mini lightning generator is what it's doing. And that's, you know, what's actually doing it each time it does that pulse. That's actually what it's doing, is it's generating that, that plasma, that lightning, by generating that, that pulse each time it's happening. Hopefully that made sense.
Yes. Okay.
Okay, I'm gonna try and share another video. I'm trying to see if I can get it to come up. Let me try this real quick. I might be able to do it this way. If I can share my screen. No, that's not gonna work. Let me try it this way. Sorry about this. Can everyone see the video on my screen now?
Yes.
Yep.
Okay, I'm gonna see if I can rearrange this a little bit, make it easier to rotate. Sorry, tried to have this set up before, but Zoom doesn't like it when you do more than one video at a time for some reason. Let's see if I can rotate it one more and then rotate it one more. Okay, and you can see where this one is when we get started, how it's kind of leaning up sideways. Well, this is the cloaking device. I'm shooting the plasma against the cloaking device. And in case you're not able to hear it, in a minute here, you'll see a laser where I'm actually guiding the plasma onto the cloaking device with the laser. And you'll actually see how the metamaterials, the cloaking device, is actually it's kind of splitting up the signal from the laser itself. It's splitting up the light coming from the laser, because it not only functions as a cloaking, again, invisibility cloaking, but it's also a collection of the energy that you're, you know, it's going to collect that energy from either the plasma or the laser, but it can also bend it. So it's going to bend it in another direction. In fact, they use metamaterials a lot for things like holograms and that sort of thing. So here we go. Let's see if this will work.
Okay, so here's the initial test.
Can,
the plasma.
Can you hear that as well?
Yes.
Okay, great.
Tesla coil turned up a bit, higher frequency. We're firing against the metamaterials. You can see the lightning, the plasma right there. Firing against the metamaterials to see if that's shielding it from getting to the box. I wouldn't catch on fire. I wouldn't be doing this. And I'm wearing safety glasses. Polarized. So, being careful here. Safety precautions that we're firing against there just to see if it'll shield. It's doing a kind of a split ring resonator with the metamaterials. And now I'm going to fire the laser beam at it to see if we are able to direct any of the plasma kind of going along the laser beam here. This is the EMP cloaking. You can see how the EMP is being fired as the little plasma balls from the Tesla coil here, the lightning, fired against the metamaterials that function as the EMP cloaking device right here. I'm hoping the laser will help direct the plasma to wherever we want it to go. Like the laser beam will serve as the kind of the propulsion guide to the plasma lightning EMP coming out of the Tesla coil right here. And it looks like it is able to kind of guide the, to get it closer, I notice the noise changing too. The Tesla coil guiding it along the laser beam here. See if it's able to do that. And there's the deflection. It's actually deflecting it a little bit. Right here you can see the deflection of the light, and as the light's being also, if we move it up on the metamaterials, we can see it being kind of refracted as it would with a solar cell, which is another function of metamaterials, not just as a cloaking device for light or acoustic medium, but also as a solar cell to collect light and deflect it and serve as a lens and as an antenna to be able to send that information from wherever he goes. Also, you can bend them in the right direction, they form a hologram if you're using those metamaterials to do that as well. But anyway, just kind of testing it out to see what happens here.
Okay, any questions on that?
No?
Okay, so that was just kind of a brief demonstration of actually two things: a scaled down version of a plasma contained fusion reactor, a tokamak, with the magnetic field, and then the actual just testing out some low voltage EMPs coming from the Tesla coil as well against the metamaterial cloaking devices guided by the laser. Okay, so back to this. Here is, again, this paper where they're looking at what they call space micropropulsion systems using metamaterials and plasma, how metamaterials are being used to generate plasma, like by focusing it and creating the plasma itself, or by using plasma to create metamaterials, kind of each one going into the other. So it's kind of an interesting little paper. And then let me put this back in slide form. And then here's what we have, what's actually happening within this fusion reactor called a tokamak. And you can see on the upper left, this is what they call the JT60SA, which is a Japanese tokamak fusion reactor. It's the most powerful one right now that they're using for nuclear fusion. And you can see how they got this very strong magnetic field with these superconducting magnets containing the superheated plasma. And in the core of that is where they have the radioactive material, which is being superheated and then driving this generator here at the bottom that's producing that heat, which is, again, going to the steam turbine generator, and that's what's creating the electricity. And so this is how a fusion reactor actually works. And again, I didn't want to use or even get near any radioactive material, so mine was just strictly a scaled down version of the magnetic field with the simple plasma going around it, being contained by it. And then on the right, I apologize, this is a little fuzzy, of how fusion actually works. Is you have these heavy hydrogen isotopes of hydrogen called deuterium and tritium, and you're fusing those together with this high heat. This plasma contained by the magnetic field is fusing them together. And when you fuse them together, you get helium because you're increasing your atomic number of hydrogen, and you also get energy. And that's where the energy, the heat in the form of heat, is coming out of this reactor. And so this one here is they say it's producing about 40 megawatts. And it's but the very, very strong magnetic field, about 2.25 Tesla, which is a huge, very strong magnetic field, and about 5 million amps for the plasma current. So lots of big. Oh, sorry, did someone have a question? Okay. Lots of big energy going on there. But that's how an actual fusion reactor works. So I just had kind of a toy version of that. Now, one of the things I wanted to check against is anyone else trying to do this using Tesla coils for fusion just for the fun of it? I found quite a few like hobbyist sites and things like that were actually interested, but some looked pretty serious. And again, back to the torus shape, that's what the fusion reactor is. If you look at this, it's just a big donut. And that's what this, they're creating this toroidal coil, which is what's really happening within the Tesla coil. And using this plasma that the Tesla coil is generating, contained by a magnetic field, to actually produce fusion using radioactive material. So people are actually experimenting with this. But one of the downsides is that it's not always easy to control the plasma from the Tesla coil. But they're working on ways to contain it better. And so, yeah, it looks like people have actually seriously looked into using Tesla coils for fusion reaction. And this is an interesting paper where they're actually using plasma as a dome to cloak against an electromagnetic pulse, an EMP itself. So you're actually now using plasma to protect you from plasma, which I thought was interesting. So they're creating this dome of plasma, and they're using this to protect a radar from an EMP. So, you think of radar systems, and that's definitely one of the things that needs to be protected from an EMP. but they're using a plasma dome to protect the radar equipment from the actual EMP. So I thought that was kind of interesting. And here's some things I've made before, and I had a startup out in Arizona, and then we made metamaterials. Is one of the things we did. We did cloaking, electromagnetic black hole simulations to test things, some of the ideas from string theory out, if we could like test these electromagnetic black holes and form singularities in cloaking, using them for solar. The one on the left here is actually an antenna and a testing for a solar cell and wireless transmission. And again, the one in the middle is that split ring resonator I was using for the EMP cloak. And then the one on the right is an actual cell that we were building at the time and testing for creating holographics and also for solar cells. And this is kind of a neat thing from MIT. They talked about you could build a warp drive using metamaterials. If you're able to warp time and space, you could actually warp, as a magnetic field, and you could do it at a large enough scale. You'd be able to warp it enough to be able to get things moving, hypothetically faster than light. Of course, it would take a huge amount of energy, but they were just kind of, tongue-in-cheek saying this, but I thought it was still kind of cool. And then they're using metamaterials to simulate universe things and like black holes and things like that. And then down below is where they're doing a new type of acoustic metamaterials. You can see this entire room at Caltech. It's being kind of cloaked. They actually cloak this whole room, and they're able to contain a lot of these signals within that and be able to cloak things around it, which I thought was really cool. So. And then just briefly, I'm going to talk about LIGO, which is the Laser Interferometer Gravitational Observatory, where they have these underground lasers that they're actually using to detect things like gravitational waves, which are disturbances in space-time from very large objects like black holes and things like that, and exploding nebula and different things, quasars, and that they're getting these gravitational waves. And they have these lasers buried underground that are they're firing them at these detectors that are about 4 feet in diameter, that are about 2.5 miles away, and they can actually measure the difference between these detectors moving. They're like hanging mirrors. You can see how they kind of fire these two lasers at right angles to each other at these hanging mirrors. They can detect the movement of the mirrors within the width of a proton, and they have to be able to filter out all the noise. And they have them, there's one in Hanford, Washington, and one in Louisiana. But they have, of course, they're bringing in all kinds of noise, like seismic noise and things like that. So they have to be able to look at the right wavelength to be able to get these perturbations to figure out if it's an actual gravitational wave, because it's so small. The perturbation of it is so small. So they're figuring out ways to filter and cloak out the other types of waves that might be making these detectors move, not just the gravitational waves. And that's kind of why I brought this in. And again, I did a talk a while back on cosmic strings, which are actually one of the things they're looking for in space, which would be a string itself, part of string theory that got stretched out during the Big Bang. And they move through the universe, incredibly millions of miles long, but only about a half of a width of a proton wide. And it's kind of like you think of a stick moving through a stream, disturbing the water. That's kind of what a cosmic string does with space-time when it's moving through it. And so they're using these detectors to not only look for gravitational waves themselves, but what could be causing the gravitational waves, like, again, colliding black holes or quasars or things like that, but also maybe possibly cosmic strings. And they look at this bandwidth that's about 10 to the negative 15 centimeter, which is about 100 millionth, and about 1 to 5 hertz, so very slow. And they're thinking that that's where the cosmic string is going to be, is somewhere within that gravitational cusp right there at about 1.1 to 5 hertz and just 10 to the negative 15 centimeters, because it's really small. And I've got some links here to LIGO and things like that. But the reason I brought that up is directly related to cloaking, is you can use a lot of the same tools for doing cloaking with metamaterials and EMPs and things like that, where you can use the same mathematical tools and also testing tools as you would for looking for cosmic strings, because a cosmic string is basically a perturbation in space and time. And it's what you're going to do is you're going to cloak around something that's kind of the same thing. Different simulation models. Okay, So that's kind of where you can kind of bring in looking at the LIGO and things like that. But I also found this kind of neat paper that was done by Caltech and LIGO, that they're using trees as a cloaking device for LIGO. So in other words, they want to cloak out some of the noise that LIGO's picking up, the gravitational and cosmic string wave detectors, but they want to test and see if there's a way to filter out the rest of the noise, like noise coming from not just seismic activity, but can they cloak against even like cars on the freeway? So what they did is they went to the Arboretum, and I'm hoping everyone knows where the Arboretum is. And they did some experiments at the Arboretum where they looked at a group of trees at the Arboretum, and then they measured the noise coming from the freeway above it, like the 210 freeway, to see if they got less noise in the middle of these trees than if they did out in an open area. So if the trees were able to filter out the noise, and here's kind of the photo of the Arboretum right here where they were at, and you can see where they have these little markings. They had geophones there, and they would do it right in the middle of a cluster of trees, and then they moved the geophones around in open areas to see if they actually were able to get better data from the areas that the trees were at. In other words, they were able to filter out some of that noise from the freeway. And so I thought that was kind of a neat little experiment that they did, because they're thinking about, well, if we just plant a bunch of trees over LIGO, it's already buried underground. Will that help filter out all the other noise, like the seismic activity and stuff like that? They actually trees can function as a cloaking device. Okay, so I'm getting to kind of the last part of this, and it's somewhere here I had to put some math in here. So I'm going to kind of go over what's some of the math behind it that ties in with the other math and the stuff that I work on, as far as whether it's at Edison, even what I teach, and also what I do independently. But so that's where I'm going to kind of go with this, and I apologize. I know some people, that not really their thing, but I just will do like a very brief overview. And if anyone's interested in going deeper, I could definitely do that if you'd like to. So what this is called what I call CogFab. I just abbreviate it. And this is this mathematics, physics, machine learning theoretical framework. And what does it CogFab stand for? It's Koopman, von Neumann, Galerkin, isogeometric optics, Feynman-Kac, and ADS CFT Boltzmann stochastic brain knot theory. I know it's a total mouthful. That's a word salad, but it actually hits on a lot of these different things that I've been talking about so far, but I'll get into a little bit of it, I know, in the few minutes remaining. But I presented a lot of this over the years. The last 10 years, I've been kind of working on this, and at the Society of Industrial Applied Mathematics conferences, Caltech Numerical Relativity Group, the Southern California Mathematics Symposium. It's been at UCI and Caltech as well. And then, of course, I have PVAA in there because I know I presented a little bit of this to you guys in the past, and also with tonight. And I got links to all this stuff like on LinkedIn Academia, Google Scholar, and some other things. But what this has to do with is it's tying all these different things like cloaking, finite element methods, the wave equations, they call the Helmholtz equation, which is related to Maxwell's equations for electromagnetic fields, and then creating electromagnetic black holes with the metamaterials. How do we measure that? And I've got some diagrams here on the bottom. And we're using these tools called transformation optics, which are applying general relativity gravitational equations to electromagnetic fields. And then isogeometrics, which is using finite elements in CAD for B-splines and knots to like show nodes and singularities and things like that, and running cloaking plasma simulations. And then get applications to metamaterials, cloaking, electromagnetic black holes, plasma fusion, solar energy, space propulsion. That's the plasma and antenna. And talk about, my business developed these cloaking and plasma antenna stuff. And then what's the Koopman von Neumann? Well, it's just, it's the different theories, but the string as in string theory, that where a string is moving through an electromagnetic field is called a direct Born-Infeld action. And that's what we use also to detect cosmic strings, which I mentioned about the stretched springs in space with the LIGO detector. And I correlated that action, that string action in electromagnetic fields, to these electromagnetic finite element method black holes. And then I modified what's called the Feynman-Kac if you're familiar with quantum path integrals, if you've ever heard that, for probabilistic strings, and then showed a correlation with Koopman-von Neumann operator, which is Koopman-von Neumann operator is a way to kind of classically explain a lot of the things that's happening with gravity and things like that in a classical way without having to quantize it. But it's also a way to revise the path integrals to include classical Newtonian types of things. And it includes the same math that they use for the Black-Scholes model in economics and finance. And here's just kind of a model, because now they apply it to computer models and data, and we can take a finite nonlinear data set and we turn it into a linear data set. But the trade-off is it's now infinite dimensions, so we got to cut those dimensions down. So we go from finite nonlinear to infinite linear. And that's what the Koopman-von Neumann theory applied to data science and machine learning is. And we use this thing called dynamic node decomposition to do that, to take an infinite data set and make it finite. And we use what's called principal component analysis and Fourier series. So going full circle, this dynamic mode decomposition from the Koopman-von Neumann is the same thing as the Galerkin method is that I use for the cloaking and electromagnetic black holes. And that the hidden dimensions that we have within the Koopman thing are the same as the holographic ones, where they call the anti-de Sitter space conformal field theory, which is one of the most promising ways to actually prove not only string theory, but how to unify gravity with the other forces of nature, the electromagnetic and the nuclear forces, by saying gravity is always one extra dimension than anything in a quantum field. And then finally, it's also part of machine learning, where they have what are called neural networks. And a Boltzmann machine is just a Koopman neural network. Again, a Koopman infinite dimension neural network, but using physics. Energy values as the nodes. And a node is a knot. If you think of a node like on a network, it's all kind of tying this stuff together. And this is just a brief diagram of these different partial differential equations and how they kind of fit together with the Koopman-von Neumann. I won't go into this in any detail. I just wanted to show the diagram. But everything that's kind of tying this stuff together are the knots. I say that tongue in cheek, but it's really, the knots are non-trivial to like so many different things when it comes to like even in physics with the two theories of everything, which are the string, M theory, brain theory. Brain is just a different dimensional string, and what they call Wilson loop path integral, but it's also for loop quantum gravity, which are based on Wilson loops, or just the paths of particles through space. And then a knot can be used to be something in a black hole. It can be used in energy node, field of turbulence. Tangled string is a D brain. It's a DNA helix. They use it a lot in cryptography, molecular compound. Paths of robots or knots, stock market behavior or knots. And it could be so many different things. I just drew like a kind of a squiggly shape, turning into what's called a trifold knot, which is actually very common. And it has 3 points on it, and these each cross at different vertices of the knot. So the thing that's kind of bringing this all together is the knots, and that's what's bringing the all the different modes of the different math and the physics together. And again, back to our torus or donut shape, that the simplest torus is a circle, which is a zero knot. That's basically just what they call a circle. And that the torus in 3D is a donut with the strings wound around it. So if you think of a string just winding around a donut, that's where it kind of brings in the strings from string theory. But the D brain is a torus wrapped to form a singularity. So if you think of a flat sheet, that's just a two-dimensional string, and they call that a two brain or a one brain. A zero brain would be a point, one brain would be a string, and a two brain would be a sheet. And then just again, tori, what's within the tokamak reactor, that's what creates the plasma. In fusion propulsion systems, it's shaped like a donut. So this is all about donuts and knots, really, when it comes down to it, and all this other stuff. And just some of the applications, again, partial differential equation, fluid dynamics, cloaking, plasma fusion, energy propulsion, string theory, quantum field theory, knot theory, of course, complexity, chaos, because we deal a lot with chaotics in nonlinear systems, quantum computer cryptography, neural networks, and biology, genetics, economics. When you're looking at stocks, shocks, and singularities, that's all based on knots. And just some things even carries over into art, philosophy, anthropology, and things like that. And I just say science fiction or science future. Of course, invisibility, time travel, teleportation, quantum AI, full fusion energy. Who knows? I mean, just some stuff that's fun to play around with, even if it's still science fiction. And for those that really want to be tortured for the last couple minutes, I'll just show a couple real quick proofs. Again, if you want me to go into any more detail, I've actually, I'm putting together a kind of a work that's pulling all this together, but it's about 200 pages long. So I didn't want to, put everyone to sleep, maybe only half the audience to sleep tonight. So I'm just going to show these real quick. So we got some of the proofs. I won't go into any detail, but you can kind of just take a look at what these are kind of saying. And it's just really saying that we're doing the Schrodinger equation within a certain shape that's a knot. And we're containing the quantum field with that, and then forms this, what they call a CAM torus, which is a chaotic torus. And it's just talking about that. So I can go into more detail. And then similar theorems and lemmas based off of that, and this Feynman-Kac and the Dirac-Born-Fold action. Again, the action of a string moving through an electromagnetic field, and how the ADS-CFT is actually a restricted Boltzmann machine. That's that neural network for the energy nodes, and how we pull in the Koopman-von Neumann operator and show that it's actually part of the stochastic Feynman-Kac path integral. And just to keep things interesting or less interesting, there's just some of the math behind some of the proofs. Here's where I convert the dynamical system for the Koopman-von Neumann operator. I get more into, here's how I'm doing the transform on the partial differential equation and using this thing called a Witten diagram. If you've ever heard of Feynman diagrams, there's a guy named Ed Witten, if you're familiar with anything in string theory or M theory, is one of the top guys, and he brings in a lot of this stuff. He's the one that actually equated knots to quantum field theory. But a Witten diagram is just a multi-dimensional Feynman diagram, if you've heard of a Feynman diagram before. That's kind of what I'm doing here. And just even worse, just some more math stuff, pulling in the Galerkin method into this integral, and then showing how it's related to the Koopman operator, the Feynman element, cloaking stuff. I guess that's it. I think one more thing to show on them. Any questions on any of that?
When we have a sunburst there, what is it that Edison and you guys are doing to harden the grid?
Well, one thing that we've worked on was we do have shielding devices like on our transformers. They're just not as kind of robust as the ones that I was kind of demonstrating, where I want to scale up the metamaterials and use them. And I've actually proposed that to Edison to see if that's something that we're able to do. And the thing about metamaterials is they're flexible, so you can actually use those as shielding for conductors as well. It can be like built into like a large cloaking system over a device, like a transformer. But it can also be wrapped around a conductor. And in addition to that, they're also collectors, so they'll be collecting the energy from the EMP. But yeah, we talk about a lot of the wildfire mitigation that we've done is with burying conductors or shielding conductors with other things. But I've actually done studies at Edison where we're looking at how gamma rays are affecting the covered conductor. In other words, we have like rubber or elastic material that's shielding our conductor, and how gamma rays over time are affecting the erosion of that particular type of material over the conductor. And then what type of soil, like is the soil more acidic? Is that affecting it more? We actually bring in things like that, like the soil type, what type of soil is going to be affecting that more. And so that's part of the studies that we're doing, but we definitely want to move forward with this, continue to do research in this. I submitted some ideas to Edison, ideas what they call SE ideas, which works with prototypes and things like that. So I'm kind of waiting to hear back. But in addition to that, also doing the research with the MISA team at Cal Poly, and also some of the other things that I've done as well over there.
Go ahead.
I was wondering about the research for CMEs affecting earthquake seismology. I saw those, the paper, and it looked like some Russians names, but are places like Caltech where we all turn to, when there's an earthquake, or they have the Quake Alert app. Are they like seriously looking at that?
I think it's becoming much more relevant. Yes. It's always a joke. I know over at the earthquake center there, and again, we partner with them at Edison. We have a lot of partnerships with Caltech, but that's one of them is developing some of the sensors with them with the earthquake center. And they always say, like when there's an earthquake, they'll ask like Lucy Jones or something, and they'll say, well, has anyone predicted this earthquake? And she says, no, not yet. So that's kind of the joke is, yeah, you always hear about it afterwards, but there's a lot of work to be done still. But I think if we can look for correlations in these chaotic systems, because it really is a nonlinear chaotic system, which kind of brings in that part of the math part of the stuff that I do, that there may be ways to at least narrow it down a bit. I mean, we may never get to the point where we're able to pinpoint it exactly, and it may be not as geographically based, but at least we'll have a better idea. And I think that'll help with that. Go ahead. I'm sorry.
Thermal mass ejection, the magnetosphere will protect the Earth generally, although something like the Carrington event, it didn't do a super great job. But could there be a thermal mass ejection that really would, like P waves, or go through the Earth, and we could see it like through the magma?
I think that's what that one paper had done, is that they looked at the proton density, and they were able to actually see that it was actually affecting the magma itself, that the magma was actually, they're measuring the movement in that with the proton density. And that's what they were saying, that, yeah, when the EMP hit, that like there was a 1-day lag, and then they noticed, the magma itself would just increase in intensity in the movement of the magma by that proton density function. That's what I think they were using that for. So yeah, definitely possible.
Do you talk about earthquakes and flares? Do you think it could affect the poles flipping?
I think there's definitely, I mean, you talk about like chaos and complexity, where you talk about the butterfly effect and butterfly flapping its wings, and it's affecting a storm, half the world away. I definitely think that these, you think of things as like small perturbations that are affecting everything. It's definitely something that could be happening. I think they say what the magnetic poles are actually moving. They've been detecting it, and it's been, there's a chance that it may eventually reverse. They don't know when yet, but I think that all these things are interrelated. I really do. I mean, that we may not have all the science yet to support it, but there's enough indirect evidence to say yes, that everything is kind of being affected by something else. Something moving over here is affecting something moving over here. Definitely.
Do you expect that the moon not having magma would have very different seismic reactions to CMEs?
I would think so. I found it interesting that a moon actually has seismic activity when they're able to measure it. I don't know what, I haven't gone into detail on what the differences are, but I would think, a lot of has to do with gravitational pull and things like that, of course, being affected, whether it's us or the other guys around it, the other planets and whatnot. But I would say that, yes, definitely. I don't know of any studies at this time that have actually measured the effects of the EMP on the moon, but that's a really interesting question. Because you could kind of use that as a test case to say, okay, we're getting this different environment. And I know that they just measured the largest Mars quake recently. You know, it was like a magnitude 4 or something like that, 4.5 through the, you know, when they had their devices out there with, was it the Inquisitor or something? But it would be interesting to see how it's affecting the moon. Like what an EMP is actually hitting the moon. What is it doing to the moon structure? Is it doing anything? Is there any type of, you know, I'm sure that, you know, there's conductive material within the moon's crust and everything like that. How is it affecting that? I think it would be really interesting to look at that.
Yeah, even correlating earthquakes and moonquakes, if the, you know, if the EMP is hitting both, there should be some correlation there, I suppose.
Yeah, absolutely. And you think, even if it doesn't have magma, maybe it's, you know, it could be causing vibrations within the electromagnetic fields of the conductive material within the moon's crust. So that could cause all kinds of interesting things to happen.
Yeah. Are we able right now to study other types of stars and looking for sunspot activity and EMPs and things like brown dwarfs and red giants?
I think they've actually done a little bit with, I want to say Rigel or something, but there's been some, I'm going way back in my Rolodex right now, thinking that I've seen something related to, well, I know when they had the latest nebula explosion that they were looking how it was affecting the planets around it, or the closest proximity planets, to see how that affected with the gamma ray bursts and things like that. I know that's something they've been looking at quite closely. But I don't know if they focus primarily on EMPs. I think it's been more like when the star explodes, how it's affecting its solar system and things like that. But you think about it in this sense, when you're having, you know, like a supernova, that's just a really, really, really big EMP. And when you put it into context, that's just the star is just releasing all of its energy that's left over, and it's leaving a brown dwarf or whatever. If it's strong enough, it's leaving a black hole, you know, if the mass is big enough. So if you think of it in terms of, well, you know, we're having these little novas, that's what an EMP kind of is. It's just a little supernova. So you kind of scale that up or down, you can kind of say, yeah, maybe it would do something on a much, much larger scale. And then when you, of course, you have like a pulsar or something with a gamma ray burst, it's, you know, it's a completely different thing altogether. That's on a completely different scale. So.
Thanks. Very interesting presentation.
Oh, thank you. I had, if no further questions, I just had one last thing I'd like to show, if that's okay.
Okay.
I'm going to do a shameless plug for my, this is my website. I've got some stuff on here. A lot of it's free and downloadable if you're interested. Can everybody see that? Okay.
We see www.zerke.com.
Okay. There we go. Okay, that's my website. So this is just kind of, I put stuff on here, but I've got a couple of the books I just published in January. If you're interested, I write like horror sci-fi on the, you know, on the side, and short stories, satire, paranormal investigation stuff, just for the fun of it. I got some of my art. This is what latest I call my Van Gogh ripoff that I did. Some stories, short film I did a short horror film on Mount Baldy. It's on there, and all this is, you know, except for the Amazon stuff. It's all free. You can download it if you want. One of my other books I wrote, it's about a sci-fi time travel, military black ops, secret society stuff. That's all on here. Some of my other books on Amazon. Then I got some of my papers if you want to download. Here's my CogFab theory again that I've been working on. So it's got stuff broken down for that. Additional research, short stories. A lot of this is just free stuff if you want to download it. I've got some articles. I got stories and papers and other things. I got a children's book I wrote, emergency services, and just music, artwork, and humor. I got some of my music stuff on here as well, and some more of my artwork right here. So just, interesting if you're into that and you want to take a look, please feel free to just go into that. And I got links to this on my LinkedIn page and everything like that too as well. So, yeah.
Thank you.